Hey guys, you're watching Python tutorial videos on my YouTube channel Python for Microscopists. In the last couple of tutorials, we looked at the applications of autoencoders, and in the last tutorial, we actually looked at how autoencoders can be used to artificially colorize black and white or grayscale images. And we also looked at how we can actually denoise some images using autoencoder architecture in one of the previous tutorials. Now, for all of these applications, we found our own images and we trained the entire network from scratch. Meaning, for image colorization, we downloaded a bunch of images from Google image search and then converted them to grayscale and used those for training and so on. Well, nothing wrong with that. In fact, you probably would end up getting much better accuracy if you use your own images, provided you have thousands and thousands of images that are typically required to achieve the best accuracy that you can get out of a neural network or deep learning approach. Now, an alternate way of actually increasing your accuracy is by getting more images in an artificial way, right? I mean, you can actually take the existing images and then use the data gen within Keras, for example, and then rotate the image, flip the image, and do certain image transformation operations to simulate multiple images from one single image, and this is called data augmentation. Okay, again, this has been proven to work, but nothing beats having loads and loads of real images, real annotated images, right? That's what we need for deep learning. Now, oftentimes we do not have this luxury. So what can we do? Well, go ahead and look for some databases, data online, and then go ahead and train it. There is a lot of data that you can actually get, annotated data for free when you search online. Now, the question comes down to the fact that you probably do not have a computer that's powerful enough to work on all of these this data that you download, and work on it. Now, others have already done that. There are a lot of people who actually put in a lot of effort, and they have much better resources in terms of computation. And they spent time and effort in training this. And in fact, these are the guys who actually do research at these high-end universities. And for example, VGG16, I believe, is from Oxford. But there are people who actually put in a lot of effort in training this. So what's the point in retraining everything? So transfer learning is a way of actually taking what work has been done and actually transferring that into a different domain. For example, if you find a network that has been trained on a whole bunch of cats, dogs, buses, and like ImageNet or VGG16, so they're trained on a whole bunch of everyday things. So what you can actually do is take part of that and apply that to your specific problem, whether you're trying to classify cells or design an autoencoder. Okay, so that's a lot of talking, but let me just show you a couple of slides. First of all, look at the neural network architecture, right? So for example, the autoencoder. This is how we actually put together in a couple of videos prior to this one. I believe this is for denoising, but either way, we start with a 256 by 256 by 3 image and then increase the number of filters. Right here we have 32 filters, so we have 256 by 256 by 32 images after this convolutional operation, and then 32 images and filters and so on, and progressively we are decreasing the size of our images from 256 to 32 and then going back to 256. So we put this architecture together, and we trained our network completely from scratch. But there are networks out there like VGG16, for example, that someone put together, and that has been already trained on thousands and thousands and thousands of images for multiple epochs, and the weights are to the point where I believe the accuracy is above 99% on these for all the 1,000 classes that they trained this on. So why can't we just go ahead and use this? Now, if you ask the question about, okay, but these guys did not train this, for example, neuron segmentation or cell segmentation or separating something that you are interested in an image. Well, that's correct. But if you think about exactly what's happening during this operation, what's happening is you're actually generating a whole bunch of convolutional, applying a whole bunch of filters. Now, in layer 1, for example, you may apply a filter and then it actually starts extracting, let's say, edges. Okay. In layer 2, it starts to detect maybe roundedness or curviness of certain features. In layer 3, it starts to detect a bit more features, right? Layer 4, now you can see you started to identify individual faces of these dogs or clocks or whatever these regions are. And in layer 5, you get much better definition. So progressively, this is how deep neural networks actually work, right? So progressively, you're going from like very high level all the way down to, okay, getting down to the classification part. So think of actually taking all of this feature extraction part. If you just go back to the VGG16, from the time we input our image all the way up to the last feature extraction part, I believe this is total 19 layers up to that point, and then comes the final classification part. So what if you can chop this model up to this point and only take the feature extraction part and download the corresponding weights of the feature extraction part, right? So of all of these, then it's almost like you trained the system to learn about these edges and curves and all of this stuff on these thousands and thousands of images. Okay, and up to this point, it should be able to actually figure out exactly, learn at least from your own images a way of classifying or identifying the edges and curves and all types of different features from your specific images. Then you actually add your own classification at the end. Instead of all 1000, I think on VGG16, I know they do have like a tennis ball, a bus, a race car, and a whole bunch of others. Obviously, 1000 of these classifications that an input image can be classified into. Now, in your case, this can be a malarial cell or a healthy cell, a neuron or a dendrite, or depending on your research, this can be a austenitic stele versus martensitic stele if you have like a lot of texture in your martensite, right? So depending on your background, if you're into oil and gas geology, is this a clay structure or is this like a hard mineral, some sort of a feldspar or something else? So depending on your application, then you can add your own classification layer. In fact, in the next tutorial, I'm going to talk about how you can take the feature extraction part and then join it to the decoder. Like, remember, we started everything with our autoencoders, where we have a encoder and the decoder part, right? Encoder bins the image down to, in this example, 7 by 7 by 512, right? 7 by 7 image. And then what if we attach a decoder that takes the image from 7 by 7 all the way to 224 by 224? So let's do that in the next tutorial. So it's not just a final classification layer. You can take the weights up to this point and then add this to any application that you are trying to put together. I hope the theory part actually makes sense. So what we will do right now is jump into our Spider IDE and write a few lines of code to actually take this VGG as is and then just predict whether we have a tennis ball or a bus or something. We'll supply an image and then see how it works. Okay, so let's jump into our Spider. Okay, so and before typing anything, let me actually show you some documentation. If you go to Keras documentation, you can see that you can actually, directly using Keras, you can import any of these pre-trained networks. Like we are going to focus on VGG16 for now, but you can use any of these other ones. Go ahead and experiment with them. And in fact, if you go to GitHub Keras applications documentation, you can actually download the actual Python file. For example, if I click on VGG16, you can see the actual code behind this library here. So this is exactly what we are going to import anyway. So the way we do that is, again, this is part of Keras. So Keras.applications, right? This is the documentation we just saw. So within here we have something called VGG. As you can see, there are a whole bunch of other model. So we are just going to select VGG and let's import VGG16. Okay, that's it. So now we can just go ahead and define our model as VGG16 and we are done, believe it or not. Now we have our model. Now we have our pre-trained model. This is equivalent to us putting together our model, training it on tens of thousands of images. So we already have it right here. Now you can check it. If you're curious about how the structure looks like, you can go ahead and print it out. So let me print this out. Okay, there is the summary. And by the way, I should mention that for the first time, it actually, if you do this, it takes a little while because it's almost 600 megabytes. And it downloads the weights from the internet. And of course, while importing this, while defining this model, you can actually, if you go back to the documentation, you can see that you can mention whether let's click on VGG16 here. You can mention whether you want to include the weights or only the structure, and if you want to download the whole thing or if you want to just chop it off at some point, which we'll do in our next tutorial. But all of that can be actually supplied right here. But for now, we are actually importing everything. And as you can see, it starts with a input image 224 by 224 by 3, which means we must use an input image that goes into this network with exactly the same dimensions. Once it goes in here, then you can change things if you want. But the first thing is it's applying 64 filters and then 128 and so on, and progressively going all the way to 512. And eventually, at the end of this feature extraction part, our image size is 7 by 7 by 512. Okay. After that, it's going to flatten this, and obviously, before going to dense layer, you flatten it to convert this into a vector, and then eventually the predictions are going to happen, and there are 1,000 different classes for predictions. Okay, all of this has been done, so we are not going to train this model. We are going to take this model as is. That's it. This means now we are all actually set to load an image and go ahead and classify it. And this part is simple, and instead of you again listening me type, I actually paused the video, typed it in a text notepad. Otherwise, my keyboard is loud. So within Keras and pre-processing, you can actually load an image and you can specify a target size. So all your input images are converted to whatever the specified size. And I do have a few images that I just downloaded. Again, these are the images that we work typically. So you can see I have a cab, I have a tennis ball, and we can also try what it says. I don't think the network is trained on Einstein, but we'll see what it says if I supply an Einstein image. Okay. So the images are 224. So what do we do next? We need to convert these. So if we run this here, now you can see that this image is not in a NumPy array format. Okay. So we need to convert this into a NumPy array format, and again you can use np.array, or you can actually, if you want to stick with Keras, they have image to array, so go ahead and use that. And if we run this, now you can see now this is an array of 224 by 224 by 3, and the values are floating point 32. Okay, so that's now we are done loading the image. Now, one other thing is, I mean, in this case, I'm only working with one image, but typically what goes in is it expects us to actually load multiple images, or it's ready to accept multiple images. So the array needs to be in a shape where it knows that it's multiple images. For example, if I have 10 images, then the array should be 10, 224, 224, 3. In this case, I have only one image, so but still the input needs to be 1, 224, 224, and 3. Okay. Again, multiple ways that you can actually expand these dimensions or add this extra dimension. One way is you can basically say, go ahead and use image.reshape. And that's one way, but this is another way of actually doing. Use your NumPy expand dimensions and take your image and add at an axis equals to 0, right? So it puts 1 in front of it. So if we run this, now you can see that I have 1, 224, 224, and 3. By the way, if you're reading multiple images and concatenating the information, then that would reflect how many ever images that you are actually reading. Okay, now the other thing that we, in fact, we are almost ready. One other thing that we need to do to get better results, of course, if I supply this NumPy array to the to our model, it's going to predict it. But to improve the accuracy, we need to pre-process our images exactly the same way that they have done while training this VGG. And the way I think they did is they actually subtracted mean RGB values from the training set from every pixel in this image. Anyway, so don't need to think a lot. In fact, Keras actually made it available as pre-process input. So all you need to do is pre-process input. So if you look at the values here, oh, I cannot open that, just a second. So if you look at the values here, there are 62, 49, 41, and something over there. So now if we run this, those values should change actually. You see now it is negative 62 something. So obviously it is subtracting certain, some mean number. In fact, if I change this from, let's actually, what other image? I think the tennis ball image has a whole bunch of white background. So we'll have 255 tennis_ball. Let's actually do that. Tennis ball image, and let's run all of this. Oh, I'm sorry, up to the pre-processing part. So we have values of 255, right? So these are all bright pixels, and now if I run this pre-processing step, you should see there looks like it's actually subtracting about 100-ish from these numbers. Anyway, so the pre-processing part is taken care of, and now we are all set. We can just go ahead and predict. So the way you do that again is assign a variable predict to model.predict and image. And again, if I run only this line, it should go ahead and take a few seconds, and you see up here. So my predict is 1 by 1000, and which means I have an array of 1000 entries. And if I open this, you should see that, okay, here, whatever the 0th class is, the probability of my image belonging to that class is almost 10 to the negative 9, right? So all of these are very low probabilities. Somewhere in here, we should have something that has high probability. So so you can actually check which one it is, but that's no fun. I mean, that doesn't mean anything to us. Let's go ahead and print out exactly what the predictions are. And again, TensorFlow made it a bit easy for us to do it. So what we can do is print the probability, the highest probability, or I'm actually predicting in decode predictions. Yeah, so I'm actually predicting the top 5. Okay, so we can actually see exactly what else does it think that my tennis ball could be. Okay, so let's actually run these lines, and now you can see the, well, that's pretty good. So it thinks, well, it's unfortunate I gave exactly the same name, but it thinks that this is tennis, this image is a tennis ball with 99.88% confidence. I have no clue what Granny Smith is, and lemon came in as third. That also makes sense. Jackfruit and racket. I don't even know why it thinks this is racket, but these are 10 to the minus 5, right? So it strongly thinks that this is a tennis ball. Now let's change this to, what else do I have? A cab. Oh, it probably also comes up with a, I should have renamed my images, but anyway, let me only run this part so I don't have to download the model again. So the cab, it thinks that it's a cab with 99.9%, and then it thinks it's school bus. Well, that kind of makes sense, right? I mean, it has that look, school bus look. Sports car, well, it's very low probability that this is sports car. Now let's actually do something that's probably not inside part of this 1000 classes, which is Einstein.jpg, and let's see what it thinks Einstein is. Okay, let's run these lines again. So it thinks that it's a wig. I don't know, probably a wig. Microphone, well, his head apparently looks like microphone. Stage, feather boa. So obviously none of that makes sense. It's as accurate as the classes that you have. If I really want this to classify this as Einstein or Mona Lisa, then I would actually chop off the last couple of layers and actually retrain it to classify it as Einstein or Mona Lisa. Okay, so that's pretty much it for now, and please watch the next tutorial where we'll take this this approach. We'll take pretty much the same structure and chop off the last few layers in this VGG. I mean the dense layers, or I should say basically the dense layers and the prediction part. Only use the convolutional and add on the decoder component to convert this into a auto encoder model. Let's stick with the previous example that we did, which is colorization of images, but of course you can do any application using this. Well, I hope you found this tutorial to be useful, and I hope you learned something from this tutorial, and please experiment this on other images, other types of applications, but I hope this provided you a good foundation to build upon. If you like this tutorial, please like this video on YouTube and subscribe to my channel. Thank you very much.